Hi everyone, it's Mr. Baker here, and today we're going to be looking at alternating generators. Okay, so today we're going to be looking at AC generators, and we're going to be answering this question: how is electricity produced in a power station? So an alternating current generator, or an alternator, produces an alternating potential difference. As the coil cuts through the magnetic field, it induces a potential difference. The coil and slip rings are attached to each other. The brushes and slip rings slip past each other and make a continuous electrical connection between the coil and the rest of the circuit. They also stop the coil and the connecting wires from getting twisted and tangled. As the arms of the coil cut through the magnetic field in alternating directions, they induce an alternating potential difference. The size of the induced potential difference is greatest when the plane of the coil is parallel to the direction of the magnetic field, and it's directly cutting through those magnetic field lines. The size of the induced potential difference is zero when the plane of the coil is perpendicular to the direction of the magnetic field. So how can we increase the size of the potential difference? Okay, so here we've got another simulation by FET. It's kind of like how a hydroelectric power station might work. We've got some water that's pushing a wheel around, and that wheel's going around at 56 revolutions per minute. You can see that that's got a bar magnet on there, a permanent magnet, and the magnetic field around that is interacting with the electrons inside the wire. Those blue dots there are the electrons moving up and down because of the moving magnetic field. And then because there is a complete circuit and the light bulb is completing that circuit, you can see the rays of light there from the light bulb showing us how much potential difference is being induced, basically. So there are four ways that we can increase the amount of potential difference being induced. First way is that we can increase the strength of the magnetic field. So at the moment, the strength of the magnetic field is at 30%, whatever that is. So let's increase that to 100%, see what happens. Okay, so when I increase the strength of the magnetic field to 100%, you can see the light rays from the light bulb have got brighter, and that's because we've induced more potential difference. Let's set that back to 30. Another thing we can do is we can increase the number of loops in the wire there. So we've got 1 at the moment, let's increase that to 3, and you can see when I increase that to 3, the potential difference has increased. We're getting more light from the light bulb. Another thing I can do is I can increase the loop area, and if I increase the loop area, that will also increase the potential difference as long as the magnetic field is strong enough to interact with the electrons in that wire. And then the fourth thing I can do is I can increase the speed. So at the moment we're on 56 revolutions per minute. Let's increase that to 100 revolutions per minute, and you can see that there's more light coming off the light bulb now. The induced potential difference has increased again. Okay, so how does the voltage change on an oscilloscope display depending on how fast the alternator is turning? So let's say it's going slowly to start off with. If it's going slowly, then it might look something like this. So it is going up and down, alternating, and it's looking something like that. If it's moving fast, then that would mean that it is going to have a smaller time period, so it's going to have a higher frequency. But if it's moving faster, it's also inducing more potential difference. So we might have something that looks like this. Okay, so it's moving fast, so it's got a high frequency, but it's also increasing the amount of potential difference induced. Now, if it's going slow, but we've increased the magnetic field, then the time period is still going to be the same as this first one, but it's going to have increased the amount of potential difference induced because it's going to have more of a magnetic field, and so that's going to induce more potential difference. So it might look something like this. So the time period is still the same, but the amount of potential difference that is induced has increased. So the three side by side would look something like this. You see the top one and the bottom one have got the same time period, but the magnetic field in the bottom one is increased, so the potential difference is increased. And in the first one and the second one, the top one and the middle one, they've got the same magnetic field, but the second one, the middle one, is going faster. So that increase in speed increases the induced potential difference. A direct current generator, a DC generator or a dynamo, produces a varying potential difference that stays positive. The coil and split ring are attached to each other and move as it's spun. The split ring commutator makes an electrical connection between the coil and the rest of the circuit. They also stop the coil from getting twisted and tangled. Different to the AC generator, the split ring makes the current in the coil switch direction and then reconnect to the coil in the opposite way round every half turn, so induced potential difference does not reverse its polarity. Just like in the AC generator, the size of the induced potential difference is greatest when the plane of the coil is parallel to the direction of the magnetic field, and the size of the induced potential difference is also zero when the plane of the coil is perpendicular to the direction of the magnetic field. So this is what you should have done by the end of this lesson. You should be able to describe the operation of an alternator and identify the period and peak output voltage for generators from an oscilloscope to trace. You should be able to describe the output of an alternator and how the output voltage varies depending on its speed and the magnetic field. And you should be able to explain when the peak voltage of an AC generator is produced and explain how a DC generator works to produce its output. Okay, so at the beginning we asked this question: how is electricity produced in a power station? We looked at one example of a hydroelectric power station, but when we've got magnets moving or rotating relative to a coil of wire, if they're rotating round and round, then we're going to create positive and negative potential difference, and we're going to create an alternating current if we've got a complete circuit. And that's how most power stations will make their electricity. Okay, so this one's been all about AC generators. I've been Mr. Baker, and this has been another physics video, and I'll see you next time. Thanks very much.